Welcome to part 4 of this video series dealing with the vapor-liquid equilibrium. And in this video series, we're going to pick up where we left off from the last video dealing with the Rachford-Rice equation to be able to set everything to 0 so that we can figure out what are our 4 unknowns. And so in this one, what we're going to do is use the Rachford-Rice equation to perform a fixed temperature, pressure, flash calculation. And it's going to be for a feed of 4 moles of benzene per second and 6 moles of toluene per second, so for a total of 10 moles for the feed per second. And then the flash drum is going to be set at a temperature that is going to be 393 kelvins and 150 kilopascals. And so what we're going to want to observe and see is what are the compositions and the flow rates of the outgoing vapor and liquid phases, right? Because the feed comes in at a certain particular phase and with a composition, and then it's going to be leaving the flash drum in the vapor phase and leaving in the vapor phase. And then we want to know how much is leaving in either vapor and liquid, and what are the compositions of both the vapor and the liquid that are leaving. Now, ideally, we want to be dealing with, because we've found what our bubble temperature and dew temperatures and our bubble and dew pressures are. If we're going to have any sort of separation, it has to happen in between our bubble pressure and our dew pressure, and then our bubble our bubble temperature and our dew temperature. So we have to have any sort of separation has to happen in between these curves. And if we find that our mole fraction is greater than 1 or less than 0 for either of the phases, that means separation did not occur as we were hoping for. So we're going to go ahead and see what happens when our flash drum is set at this temperature and pressure, if separation occurs, or if it's just going to end up leaving in 100% of one of the two phases, and then but still what the compositions will be. So let's go ahead and move forward by coding this out in Python to help us resolve the Rachford-Rice equation and come down to see what the results are. So we'll go ahead and call this the Rachford-Rice equation. And our temperature, we are setting at 393 Kelvin. Our pressure, we're setting at 150 kilopascals. And then our composition of the feed is going to be, we are saying, 4 moles of benzene and 6 moles per second of toluene, so that is a 0.4 and 0.6 composition ratio. Then our feed is 10, and that is in moles per second. Now that is what we know coming in. So now we need to define our, well, what we don't know is our amount that's going to be leaving in the vapor phase. And this goes back to what we were talking about in the previous video. So here we know our ratio. Look at that. We should probably include that if we know it. Move this over. Let's put this right here. We know that our ratio is the pure component vapor pressure at a particular temperature divided by the total pressure of the system. So that is, again, the ratio, right, of the mole fraction in the liquid phase and the vapor phase, y for our y component, so the mole fraction in the vapor phase divided by the mole fraction in the liquid phase. We don't know them individually, but we do know them as a ratio because we can know what our what the pure component vapor pressure is at a set temperature or a particular temperature for each of our components divided by the total pressure of the system. And so let's go ahead and so we got that in there. Now we can look at this and see that right here we know our feed composition, we know our ratio, but we don't know what how much vapor, how much is going to be leaving in the vapor phase. What mole amount, what mole fraction amount is going to be leaving in the vapor phase from our flash drum right here. So how much is going to be leaving in the vapor phase? And that's what we need to be able to resolve. So if we can find and set our vapor phase to feed ratio, if we can find what value of this, what amount of this, like what does this value have to be to set this side to 0, then we'll know what the vapor to feed ratio is. Because we know all these other values, if we can figure out what does this have to be, knowing these other values, what does this have to be to set this side to 0, because it equals 0, then we'll be able to know what V is. And so that leads us to coding out a root solver. So let's go ahead and define our root solver. We're going to call it Rachford Rice with our vector of array of vectors. And then what is it that we're wanting to know? Well, we want to know what is it going to be where our VF, our vapor mole fraction amount to the feed ratio, what does it have to be that sets the whole thing to 0? So that's what we're doing there. And then, so we want to return, what are we returning? We're returning this right here. The sum of this. And we want that to equal 0. Okay, so our MP sum, and it's going to be, we've got Z times K minus 1, and that whole thing is going to be divided by 1 plus BF multiplied by K minus 1. There we go. Okay, so now we need to, we'll set our root for our equation. The root solver takes in an equation and it takes in an initial guess. Let's let our initial guess say, let's say half of, at this particular temperature and pressure for the flash drum, let's say half will exit as vapor as our guess. I need to put that in brackets. And we're only wanting to snag the initial array for X. Now, before we run this, we want, if separation occurred, then this will be between 0 to 1, because that means some of our ratio, some of it left as vapor and some is leaving as liquid. If it's less than 0, that means at this temperature and at this pressure, everything is leaving as liquid in our flash drum, and that means no separation occurred. If this is greater than 1, then it means that everything is leaving the flash drum as vapor, and again, no separation occurred as we were hoping for. And so let's go ahead and see what VF is. Okay, so this is greater than 1. At this particular temperature and this pressure in our flash drum, we see that we're not getting that separation because this is greater than 1. Let's just go ahead and see, we'll code the rest of this out, because with this being greater than 1, what we should then see with the Rachford Rice equation is that it should produce a negative number for our amount leaving in the liquid phase, and it should lead to a positive number for the moles of vapor leaving in the vapor phase. So let's go ahead and see if that's the case. So our V equals, well, this is V divided by F, so it's just going to be VF times F. It's going to get us there. Our L equals, so the amount leaving in the liquid phase is just whatever the feed is minus whatever's leaving in the vapor phase. Again, that's why this should be a negative number based off of what our result was for this being greater than 1. If everything is consistent here. Our X, composition in the liquid phase, mole fraction in the liquid phase, the composition is going to be, that's going to be Z divided by 1 plus VF times K minus 1. And then our y is just equal to our k times our x. Now let's print these values out. So we're going to do this. We want to output a string, print out a string, total vapor to feed ratio. And that is going to equal our VF. We want to know our total vapor in moles that is going to be leaving. We want to know our total liquid in moles. This is distracting. There we go. It's going to be leaving our flash drum. We want to know the composition of the liquid composition and in the vapor composition. So how much benzene is existing in the liquid phase, and how much of toluene is existing in the liquid phase, and then again how much benzene is in the how much of the vapor consists of benzene and how much of the vapor consists of toluene. So let's see here, liquid. What do we want to call it? Just liquid composition, liquid. Yeah, we could say liquid composition is fine. And then equals our x. And then we can say what is our vapor composition? And that is going to equal our y. And this is consistent with what we were expecting because the vapor to feed ratio is greater than 1, which is not physically possible. It just basically means, according to the Rachford equation, it's got to pump out a number. But what it actually means in reality in the flash drum is that 100% of, let's open this up right here, 100% of what's leaving our flash drum, so what's coming in through our feed at the temperature that we've set, and we've changed this now to being 393 kelvins and 150,000 pascals. So at this new given parameters, does separation occur? Well, we see it doesn't with the values that we've given. It's just showing that at that temperature and pressure, it's all leaving as vapor. It's all leaving the flash drum as vapor. And that is confirmed by seeing here the total that's leaving in the liquid phase of moles is negative, but we're not actually having a negative consistency of something. It just means that nothing is leaving in the liquid phase. And then what is also fascinating, though, to be able to see here is that in our liquid composition, the mole fraction of our liquid components here in the mixture is 0.116 of benzene is existing in the liquid phase, and then 0.88 is existing in as toluene in the liquid phase, and then 0.22 or 0.23 is benzene, and 0.77 is toluene. And that makes sense here that the vapor would be higher of the benzene content because benzene is the more volatile component, and so this agrees with what we're expecting there. But if we're wanting to get greater separation, we'd have to change our temperature and our pressure in the flash drum to have it be in the window of between our bubble and dew temperatures and pressures for the diagrams here that we've graphed out. So this video was able to show did separation occur, and with this set right here, with this set temperature and pressure, what are the compositions, which we showed down here, the compositions right here. of benzene and toluene in both the liquid and vapor phases, and then what are the flow rates of the outgoing vapor and liquid phases. And that was the really fascinating thing that Rachford Rice allowed us to do as a flash calculation, was saying, knowing our feed and knowing our temperature, what are our four unknowns, which is how much is leaving as liquid, how much is leaving as vapor, and then what are the compositions of both. And that is what we've been able to solve here in the last two videos. And so in the last video of this video series on vapor liquid equilibrium, we're going to move forward with talking about the lever rule and just to wrap this series up. So I appreciate you joining me here and look forward to seeing you in the next video. Thank you.